It goes. All right. It's my pleasure to introduce Di Chi from Purdue, who will give the seminar today. Di received his PhD in 2017 from Courant, where he worked with the late Andy Maida. And he stayed on for 4 more years till 2021 as a postdoc. And in 2021, last September, he joined as an assistant professor in the Department of Mathematics at Purdue. His research interests span a vast variety of topics, but mainly on uncertainty quantification, machine learning methods, and statistical analysis of turbulent flows. Di, it's a pleasure to have you here. Floor is yours. Please go ahead.
Okay, great. Thank you. Thanks for coming, and thanks, Mohammed, for the introduction and the invitation. So today, I'd like to discuss with you some strategies I have been working on for modeling and also for the development of effective numerical methods for turbulent dynamical systems. So it was started by Andy Maida, and I began to work on it first as a PhD student and then as a postdoc with Andy at NYU. And also recently we try to improve this method with some data-driven component. So this is a work together with John Halim at Penn State. Sorry. Somehow my computer just froze. I cannot turn the page. Let me stop sharing for a moment and restart again. Sorry about this. Full screen. Okay, great. So now let me first give you a brief overview for the challenges we have when we are dealing with these so-called turbulent systems. So generally speaking, when we want to solve or predict turbulent dynamical systems, we need to propose a probabilistic characterization for the state of variable of interest. So the reason for it is, first, the model usually are characterized in a high dimensional phase space, and also it contains high level internal instabilities. So as a result, the small errors initiated from the initial value of the boundary condition and the external excitations will be amplified in time as the system developed. So the trajectory-wise prediction will be impossible. So considering this from the other approach, we are seeking the prediction of the statistical quantities rather than a pathwise prediction. So that's one of the main topic we consider in uncertainty quantification, or in short, UQ. And here, so in this talk, I will illustrate the basic ideas mostly under the framework of geophysics systems, but indeed, as I will show you, this general framework can be applied in many nature and engineering systems, such as plasma physics and in other fields. So here I give you, let me illustrate this with this example from geophysics. And what I show here on this figure is a large-scale ocean movement. And in fact, the white strips illustrate the streamlines of the ocean flow. So it is a velocity field. And you can observe a large-scale ocean jet. So that's a meandering strip here. And that's the central quantity usually has a large impact in our daily life. And that's the thing we want to predict. But at the same time, we also observe there exists the vertices in different scales. So we can see the large, small vertices interacting with each other, and most importantly, they are coupled together with this coherent large scale structure. So this forms this one of the fundamental difficulty we need to face in addressing such kind of complex systems. So on one hand, like in weather forecast, the central object to predict is let's say the amplitude and the direction of the large scale jet. But at the same time, in order to do this, we have to dive into the smaller and smaller scales to resolve all these noisy small vertices, because even though they are small in each individual component, but as a whole together, they will have strong nonlinear feedback to the coherent large-scale structure. So it will then end up with a very computational, challenging problem. And as a result, if we turn to the statistical model or to describe the probabilistic distribution, it will usually include highly non-Gaussian statistics rather than a Gaussian one. So this is additional challenge here. And to put the goal in general, we want to propose a uniform framework that has the ability to predict the central statistical variability in this system, and it should have the ability to capture the equilibrium statistics, and more importantly, the model responses to the general form of perturbations, given the uncertainties in the initial value and in the external forcing. So here is the outline, and I would like to start with a general statistical formulation of the model, and then show you the idea to develop a reduced order method, and the second component to incorporate machine learning tools into this framework to help us expedite the process. And finally, if time permits, I would like to also discuss another group of important features that is called intermittency, and it is related with extreme events that is quite common in turbulent systems. Okay, so please interrupt me if you have any questions, and I'm happy to provide more details at any point. So to start, this is first general formulation of the system. So we denote the system of interest as U. So U is viewed as a random process or a random field. And here we just assume it's finite dimensional. So this can be viewed as a finite dimensional projection of a continuous system. But in general, then the dimensionality of the system is very large. And the dynamics of the state variable U is summarized in the way like this. So on the right-hand side of the equation, first it's subject to linear effects, and usually we decompose it into two parts. L is a skew symmetric energy conserving linear effect. So it is usually used to represent rotation, dispersive waves, and so on. And D is a negative definite operator. So it's dissipation damping effects from the flow, and the forcing from the external driving terms also in convention is decomposed first into a deterministic forcing, and also we represent the various unresolved forcing effect as a white noise process. And most importantly, the nonlinearity of the system is summarized in this quadratic bilinear term denoted by B of U and U, and usually it will satisfy some conservation law here. And in this abstract system, I just denote it as the inner product of U and the quadratic term to be 0 for all the time. So this is a general formulation, and let me give you first several examples to show you the general structure here. And I will use these examples as illustrating model for the methods later, but they both have the geophysical background. And yeah, let's first see these models. So the first model is the Lorenz 96 system, and it is proposed to imitate the mid-latitude atmosphere. So the basic idea is it is used to represent a one-dimensional circle in mid-latitude, and it is a 40-dimensional ODE system. So it is to put 40 grid points on a latitude circle. So the number 40 is proposed because in mid-latitude, if we put 40 points, the distance between two adjacent points is relatively one characteristic scale of the mid-latitude waves called Rossby waves. So the advantage of this model, first, as you can see, is simple enough. So it contains a nonlinear coupling term, which conserves energy, and linear damping and forcing. And on the other hand, we see this model has the skill to generate quite different dynamical regions by only changing the model parameters. So here in this example, we just alter the values of forcing F here, and we see in the first line and the second line quite different statistical solutions. So the first one is just the time series in space and time. We see with a relatively smaller forcing, it gives regular waves, and when we increase the value of F, it gives more homogeneous turbulence. And if we look a bit deeper about the statistics, so in the first case, it gives first two dominant modes and other modes with relatively small energy. And if we look at the PDFs of the leading mode, it shows extremely non-Gaussian statistical features. And if we look at the autocorrelation function, it oscillates for a long time, meaning that it is related with its history for quite a long time. But in the other case, there will be widespread energy spectral and a near Gaussian distribution and rapidly decaying autocorrelation function. So it can provide a wide spectrum of different statistics for us to test. That's why this is a popular model to use to test the methods in the first place. But of course, it's useful to consider some more complicated models closer to realistic. And here I just propose another model that is commonly used. It's called the quasi-geostrophic model. And it is also used to illustrate the wave in ocean and atmosphere. But I don't need to remember the complicated form of the formula, just to show you it contains also a quadratic nonlinear term. Here is represented by the Jacobians, and the linear effect beta is for the rotation. The next is for the background mean flow, which introduce instability to the system, and the right-hand side are the damping and forcing terms. So here, what I want to show you is just the typical plot of the flow snapshots for these two variables. And again, we see by altering the model parameters, we see quite distinct flow structures, and this provides us rich resources for testing different methods. And in particular, here we observe the transition from homogeneous turbulence to anisotropic zonal jets, and that's one of the issues people are interested in and want to predict with accuracy. So these are just examples, and yes, so for this model, so if we want to run a single trajectory simulation, it is still affordable with the present computational power, but especially now if we want to resolve the statistics, then we need from the direct method to perform Monte Carlo simulations, and this will require a very large ensemble size and will soon become exhausting, even though for this moderate level model. Then we will propose some other approach to represent statistical features. So in the direct way to characterize this model, we could derive the Fokker-Planck equation for the state variable, and then it will end up with a complicated high-order PDE system. So it is again even more complicated. And the strategy we take here is instead to take one step backward to consider each order of characteristics of the PDF, say the first and second moments. So we try to derive the dynamical equation for the statistical mean and covariance. And here I directly show you the resulting equation. So here P is the probability distribution characterizing U here. And so U bar is the mean of the state. And we usually do this decomposition for the state variable. So first separate the statistical mean state, and then we propose a set of bases here. And you can view the VI as a POD basis and fixed in time, and ZI becomes the stochastic coefficients that characterizing the uncertainty along each direction prescribed by the modes. So the second moment is defined by the second order expectation of the stochastic coefficient, and we get this resulting dynamical equation for mean and covariance. But looking at this equation, we will find that the model can never be closed under this way. So that is again due to the nonlinear coupling term here. So in the mean equation, we say second order moment. And if you look at the second moment equation, there is this higher order nonlinear term. So let me show you more details about this equation. So first, the mean equation is subject to the coupling term from the covariance, and B is a nonlinear coupling term here between different modes. And just as a comment, here we need to take the summation of all the subindices I and j. So in a high dimensional space, when I and j both from 1 to a large number n, this will be very computationally challenging when the dimensionality n of system increases. And more importantly, when we look more detail at the covariance equation, first, it's subject to this linear or quasi-linear operator. So this is an explicit form for it. It includes the linear coupling between different directions, but also includes the nonlinear or quasi-linear coupling between the mean state and the fluctuation mode. And the last term is just due to the white noise forcing. And the most important one is this QF. This is due to the higher order moments. So here, because the quadratic nonlinearity, the second order moment equation includes the third moment of the stochastic coefficients, and it requires the summation of all the wave numbers. So on one hand, this part is very crucial to drive the system into equilibrium. So we need to compute all these terms, and they have an important feedback to the dominant scales of the model. But at the same time, on the other hand, these are very expensive to compute directly, because we need to consider all the third moments, and it includes expectations. So high model error will be included if we try to do the directly. And so this will be the central quantity of interest we need to approximate in the development of reduced order models. And here is just a side comment. The conservation law is preserved in this statistical formulation, and we will use this later. So next.
I have a question. Do you use some kind of normalizations to kind of represent higher order term instead of computing all the statistics?
So it's a question whether we use some approximations to approximate this QF term. Yes, so that's one of the main task I will discuss next. So that's to use some low order term to approximate this higher order flux. And we need to be a bit careful if we want to introduce model errors in this term. So is this the answer? Okay.
Yeah, okay. By the way, my name is Kazi Ito.
Hi. Yes, thank you. Okay, great. Now, let me introduce the ideas to introduce the reduced order model. But first of all, let us first look at the true energy mechanisms in such kind of system in the mean and covariance dynamics. And this diagram just have a very crude illustration of the energy flow in the system. So first, we look at the mean equation. The forcing injects energy in the mean, and then the mean and the covariance in the starting time are coupled through this quasi-linear operator. And usually we can decompose the quasi-linear term into the two subspaces, and they are characterized by the sign of the eigenvectors and eigenvalues of this operator. So actually, these are the Lyapunov exponents. So when they have positive Lyapunov exponents, the initial value will be amplified in this subspace, and in the other part with negative Lyapunov exponents, the energy will be dissipated rapidly. And then this is just for the starting time, and when the energy level developed in time, there will be third order moments take over. So here is the crucial rule of the third order moment. It extracts the additional energy in the unstable subspace and inject it back into the stable one to get dissipated, and then finish the energy circle. And this is another way to show the central role in the nonlinear term here, and that's why we cannot simply ignore it. And for the reduced order model, we start with this simple truncation of the original variable to restrict it in a much lower subspace. So the reduced model becomes in this low dimensional subspace. But the central role here is still how to estimate this nonlinear term, a higher order feedback term, including higher order unresolved feedbacks of the system. So coming back to the energy circle here. So this is the exact energy circle in the exact true model. And in the imperfect model, the idea is to introduce some low order approximation to this original nonlinear flux term. And the basic idea is to follow the mechanics in the third order moments. So we decompose this into two parts. One part is negative definite. So it acts as a similar rule to extract the additional energy in the unstable subspace. And another part is positive definite to inject energy to the stable one, and then these two need to be connected to have the equivalent role as the original term. So here, let me talk about the basic idea to construct this term. So we follow several steps. So first one, as before, we decompose model approximation nonlinear flux into a negative definite one, which will act as an effective damping, and one positive definite part, which will act as an effective noise. And then we need to compute the explicit form of this operator. And in general, it's impossible or very expensive to compute it because it includes all the higher order moments. But observing this structure of the equation, actually, we can find a way to compute this term at equilibrium first without so high a cost, because when time goes to infinity, the left-hand side will vanish. So we will be able to approximate this term at equilibrium using the lower order moments. So we can have the first estimation of this term only use the equilibrium statistics of the system. But this will not be enough, because our main goal to construct this model is to capture the sensitivity, that is to capture the response or the deviation from the equilibrium state when there's perturbations to the system. So we need to introduce additional corrections to the system. And then for the additional corrections, we need to introduce additional model parameters. And then the next major task is to find a systematical way. And for example, in this case, in the first step, we could introduce one additional damping and additional noise to the system to imitate the insensitivity of the system. And then these are the parameters we need to estimate. So to do this, we again separate it into two steps. The first is to guarantee the model fidelity. That is, we need to make sure our imperfect reduced order model will be able to converge to the unperturbed statistical equilibrium when there's no perturbation to the system. And this requires the convergence of the model flux term to the true model equilibrium. And to do this, we introduce this statistical energy principle that's used the conservation law that is guaranteed in the original model, but here we introduce a statistical correspondence of the conservation quantity. So here, this energy is defined as the energy in the mean state and the total energy of the covariance, which is the trace of the matrix. So it can be found the statistical energy follows a very simple equation, and especially on the right-hand side, it is only related with the mean state, but the energy contains both statistically in the mean and the second order moments. So it gives some estimates of the total energy bonds, and so estimates for the bonds in the mean and the covariance matrix. So I skip some details for this, and the more important part is to capture the model sensitivity, meaning that we need to make sure the reduced model maintains the scale to capture the statistical responses when the forcing perturbation is applied. And in order to do this, we consult several theories. First is the linear response theory, and here's a very brief illustration for the idea here. So when we consider a dynamical system with a perturbation on the right-hand side, so what the response theory tells us is the expectation of any functional can be expanded at first, the expectation according to the equilibrium measure, and then a leading order term. And the leading order term can be written as a convolution of this so-called linear response operator and the specific forcing term. So the advantage of this linear response operator is that it is only related with the unperturbed equilibrium measure and independent with the specific forcing perturbation forms. So if we can approximate this response operator only using the equilibrium measure, we are able to at least recover some of the responses due to the different types of perturbations. So this can construct a model under a unified framework. And another ingredient is to find a proper metric to calibrate the model errors in this. So we use this relative entropy. And another advantage of it is we can use the relative entropy to measure the so-called information barrier, that is to give us an estimation of what the best error we could achieve in this model. So let me directly show you some results. So we first tested it in this L96 system, and first we propose different kind of forcing perturbations. So here we have the this ramp type forcing. So it can be viewed as a kinetic change from one state to another, and also periodic forcing like the seasonal forcing, and another is a random forcing here. And here what I plot is the model errors with different model parameters, and we see the model errors can be minimized uniformly regardless of different types of forcing perturbations. And more interesting example is in this quasi-geostrophic model, and the true statistics, we recover it using a direct numerical simulation. And this is a three-dimensional model, and we just use a moderate resolution, so 256 and 256 in the X and Y horizontal scales, and 2 layers in the vertical scale. So still it is already quite a high dimensional model and expensive to run directly. And in the reduced order model, it just takes the first 10 leading modes. So it only accounts for a very tiny portion of the total modes of the system. And we can tune this in the parameters under the information metric, and we see the model errors can be minimized under this framework. And to show you the results, so here we test it in the zonal jet region, and the thing we want to check is we perturb the forcing and see whether this reduced model can capture the responses in the jet amplitude. And here we plot the result. So the black line, so the dashed line is the equilibrium spectrum, and the black line is the response with perturbations. And the red line is the reduced model prediction with only the first 10 modes resolved. And we see it can actually capture the responses in the most energetic modes, and also it can capture the total energy structure. So this is the first part. And here we propose a parametric model to effectively or efficiently resolve the various unresolved small-scale processes. But still the tricky part here is we need to tune a series of model parameters, and it will become more and more expensive when we want to deal with an even more realistic high-dimensional system. And this will form some still high computational cost. So that's the reason we would like to try from some other approaches, and especially using a model, data-driven approach, so that we do not need to tune all these model parameters, but to learn these structures directly from data. So that's the thing we are trying to do now. And first overview about this idea, I summarize again the challenges we need to deal with in computing a turbulent system. So to find the statistics, we need to compute non-Gaussian features, and also it is multi-scale. So there are, even though we are interested only in the most dominant scale, but we need to resolve a wide spectrum of smaller scales, and it will mostly likely end up with the curse of dimensionality. And on the other hand, for the machine learning strategies, so the basic idea is to propose a combination of simple linear nonlinear functions to approximate very complicated structures, and it shows very powerful expressive power in a variety of fields, and it has a lot of successful cases already in learning dynamical systems. But here, in our case of turbulent systems, there are several additional challenges. So first, we need to deal with multi-scale structures. So if we just treat the machine learning method as a black box, it is difficult to resolve the different scales altogether. And at the same time, because we already understand some of the physics processes of this model, so it's not worth it if we just abandon all these physics understanding to only consult the machine learning tools. And also in the data-driven model, we usually don't have all the data for turbulent signals. So usually what we have is just in part of the region or part of the time of the system. So the question or challenge is, how can we use only partial data to resolve the highly complicated high-dimensional system? So here it's just a first approach to address this problem. So we propose a multi-scale model to resolve the non-Gaussian small-scale dynamics, but at the same time, we also want to consider some of the physics in the resolved scales and combine them together. And another case is to deal with the instability in the turbulent model, because again, when the instability inside system increases, it's usually very challenging to keep the system numerically stable if we want to integrate or iterate the model for a very long time. So this is another issue we need to deal with when we want to model a turbulent system directly from data. So the general idea, we come back to the statistical formulation of the model. This is the same model. I just rewrite it in a different way to fit into the machine learning framework. So in the mean dynamics, I just summarize the variance, covariance feedback in this process phi, and theta is here are the moments feedback in the covariance equation. And also we have the energy equation together. And the basic idea here is, so we keep the linear and quasi-linear dynamics explicitly in the large scales and use a neural network to learn these unresolved scales from higher order feedbacks. And especially, even though these terms include a high dimensional variable in various small scales, but this is like an embedding to a low dimensional subspace. So we can propose neural networks to approximate the combined small scale feedback in the mean and in the covariance. And this can actually fit into the more general Mori-Zwanzig formalism. So just to put it in a more general way, so we can decompose the system into resolved process and unresolved process represented by theta here.
So I have questions. You said neural network. Will you have a specific form or the more advanced form in a sense?
We use a recurrent neural network, LSTM. So I will talk more about later. And but yes, it will have a specific form because we need to deal with the multi-scales included here, and also the instabilities there.
Oh, I think instability is the most important, huh?
Yes, that's right. So yeah, I will talk more about that later. So generally speaking, if we just use a neural network directly for that, it turns out what we observe it will be numerically unstable, meaning that it will diverge very rapidly. Yeah. So yeah, I will talk about this pretty soon. So thank you.
Thank you.
Oh, sorry. Okay, so here in the Mori-Zwanzig formalism, we put the unresolved process as an expectation conditional on the history of both the resolved and the unresolved processes, so that this becomes a non-Markovian embedded map. So usually there first model formation for the signal given all the histories of the variables, and also there's a noise term to as a correction to the model error, but this is not so important here. So you can just ignore this for a moment, and we can have first estimation of the model approximation and the true trajectory. This is actually a rather crude representation and dependent on the exponential of time t. But if we look at a moderate forward time t, this is enough for our method to have the error controlled. So this is just the general theory, but let me just go to the construction of this model. So the basic idea here is we want to train the neural network with only samples from the linear response operators. So in this way, we don't need to train the extensive large data set, including all different forcing perturbation scenarios. That's to keep some of the original ideas in developing a reduced order model. But in the prediction stage, we want to check the model's scale in different kind of external perturbations, like in the previous case. So that's what we test here. So in the training stage, we use data only from the unperturbed equilibrium. So we use the invariant measure and use that to construct the response operators, like shown here. So it's just in a short period of time, but it will include the transient state of the system so that the nonlinear dynamics can be contained there. So we have enough information to train the system. And then for the prediction stage, we want to use different initial and also in the training data, we usually use homogeneous training data. That is, we use the forcing that is homogeneous in time and space. But in the prediction stage, we want to test the model prediction scale for inhomogeneous scenarios that is beyond the training data set. That's a setup of the training and prediction data. And the question is to test the scale that in the optimized neural network to predict the nonlinear statistical responses in the mean and covariance without using the explicit parameterization schemes like before. And this is the part, again, to guarantee model consistency and sensitivity, especially considering the instability of the system. And for the model consistency, like before, we need to make sure the neural network, in this case, will converge to the equilibrium statistics when the forcing goes to, in the forcing perturbation goes to 0. So this leads to an additional penalty term in the loss function to optimize. And here is important idea to model instability. So we use so one direct way we approximate is to just use a neural network to replace the unresolved part. And the problem here is the nonlinear feedback usually contains internal instability, and it is difficult to learn directly here if we just replace it with a neural network. So what I do here is to use a similar idea like previously to develop the parametric model. So we decompose it into two parts, a negative definite part to imitate the negative definite component and a positive definite component for the stable part. Then we use neural network to specifically fit in the damping and the additional noise term and construct the effective damping and the effective noise, then combine this together so that we can stabilize the linear instability of the system and then adding the more judicious amount of noise into the system. Here is some more details about the neural network, and we just take the standard long short term memory because it's a direct model to use to fit in the sequential data. So here we just take the standard structure, and the loss function is to measure the L2 loss in all the unresolved feedback terms. And we do our first test also in this analytic system first. And here is just explicit formula for this model. And again, we test the different forcing scenarios with the upward ramp forcing, downward forcing, and the periodic forcing. The unperturbed statistics is the blue line for the energy spectrum, and the resolved modes is just from k equals the wave number equals k equals 6 to k equals 12, I think. So it's just a small portion of the system and not even cover all the unstable modes. So it's a very extreme reduction of the system, and we see the prediction scale, and it captures the responses when the forcing is perturbed in both directions and also in the periodic forcing. And here's some more detailed comparison of the model errors in each mode, and it appears, at least in this simple model, it can capture the sensitivity in each in the most energetic directions quite effectively. So that's our first test. And at last, I would like to tell a bit other application of the similar idea for the prediction of intermittency and extreme events. So here is for the intermittency, some backgrounds. So one way to quantify the intermittency is to plot the PDFs of the state we are looking at. So here is this two examples. We plot the distributions. These are actually, I think, the observation data from the water vapor anomaly and the CO2 anomaly. And in convention, usually we plot it on the log coordinate. So Gaussian distribution is a parabola, and the data shows the linear long tails here. And this means the occurrence of extreme values is much larger in probability than the Gaussian. So it infers the occurrence of extreme events. And then the question is, first, what's the mechanism to form this kind of fat tails? And second, whether we can again propose some efficient models to predict this probability in extreme events. So we still start with the simple model framework. So we use T here to represent the density of the tracer field. And V is the advection velocity. So it could be the solution of the turbulent model. And on the right-hand side, these are the dissipation and the damping effect. So in the first place, we introduce some further simplifications. So in the tracer density field, we assume there's a background mean gradient and a fluctuation term. And first, for simplicity, we assume the velocity is decomposed in two parts. In the x direction, it's just a cross-swept, dependent on time, and there's a shear flow. So we can simplify the tracer equation in a form like this. The advantage of this model is we can write down the explicit solution of such kind of system given the solution of the advection flow. And this is a way to first give some explanation for the occurrence of extreme events. So here we just rewrite the same equation, but under each spectral mode. So this is each Fourier mode of the tracer if we assume periodic boundary condition, and the modes for the shear flow and the dynamics for the mean cross-swept. So the advantage is now we can write down the explicit solution for the tracer given conditional on the realization of the mean flow U here. And we see that it follows a Gaussian statistics, but depending on the realization of the large-scale mean flow U. So we see it has mean 0, and we can compute the conditional covariance explicitly here in this form. So looking more details of this expression, the first part is due to some small scale dissipation. So it is a tiny term, and this is the important part. So in most of the time, when U, capital U, is in finite amplitude, the denominator is finite amplitude, so the covariance or variance can be controlled. But there could be occasional case when the value of capital U goes to near 0, then the denominator will be extremely small value, which end up with a very large covariance from this formula. So as we can see from this test plot, the last row is the time series of the velocity, and the middle row is the time series for the tracer field. And we see every time when the velocity goes approach 0, there will be extreme events triggered. And furthermore, this is just one conditional distribution, and the final distribution is an additional integration for the conditional Gaussian distribution, adding all the Gaussian distribution together. So this gives a large phi tails here. So this is just to use a simple model to try to find the background mechanism here. And still, we want to think about the more realistic case when the advection flow is more turbulent and more complicated. So we use this quasi-geometric model as advection flow here. So it's more complicated than the previous prototype model. But if we look at the velocity field, we can observe some comparable features here. So there's actually the computation of these two typical domains, and one domain is blocked domain. So the zonal flow is mostly blocked, and it's mostly vertical meridional flow in this case. And in another region, there's a dominant zonal flow. So this can be compared with the large scale mean flow U here. So there's one region when the zonal mean flow is dominant, so the flow, the tracer will stay in small amplitude. But in this case, it is blocked, so the zonal flow U goes to very small values. We can see high spikes in the tracer fields are triggered. So this is a comparable mechanism, even though we are using the much more complicated model. And next, the question is whether we can use a similar idea to model this process. And then we just construct the reduced order model using the similar idea as before. But here we propose a stochastic version of it. And we use the same way to approximate the reduced order model damping and the noise terms. Here is some calibration strategies, but let me skip the details and show you the results. So in this case, again, we see the blue line is the true model. So we run the high dimensional model, and we get first the trajectories of tracer field, and also we can plot the PDFs of the leading mode. And in the reduced order model, we again just take the first 10 modes and use the correction term to the system. And first we see in the trajectory, the bursts or the intermittency are captured, at least qualitatively, in the two leading modes. And if we want to have a quantitative comparison in the PDFs, we compare the tails in the true model and in the reduced order model approximation, and we see the phi tails are captured in all the leading mode to a large extent. So still, this is a first test case, and next question is whether we still can generalize it into the more general framework and also add the machine learning tool to this higher dimensional, more practical models. So this is a summary. So we start with the imperfect model, and we do model calibration for equilibrium fidelity, and also to use the sensitivity analysis to capture the model statistical responses subject to the generalized false interval. That's to use the information framework. And also this is something in progress now to develop a data-driven component into the reduced order model framework, and to apply it to more high-dimensional systems. And also from other approach, this can be used to predict the intermittency and extreme events seen in passive tracer fields and in the related problems. So that's all. Thank you very much.
Well, thank you very much, Dee. Let me stop recording at this point.